All right. So today we'll start the link layer. So far we have done application layer, transport layer, network layer. Finally we come to the link layer. We won't be doing the physical layer in this course. So what we're going to do today is we'll just go over the basic services offered by link layer protocols, and then we'll look at two important features of link layer protocols, and I'll try to explain the concepts behind those features. One feature is error detection and correction. So link layer protocols often offer both error detection and correction, and I'll try and give sort of an intuitive understanding of how that is achieved. And the second thing that we'll look at hopefully today we'll start looking at is media access control protocol or multiple access protocols. This is a very important feature of link layer protocols. So let's first look at link layer, where it operates. So the link layer or the data link layer operates between two physically connected nodes. So far when we have looked at application layer or transport layer or even the network layer, the communication that happened in those different layers was not between two physically connected nodes. Application layer, that communication happens between processes running at computers that are far apart, that could be far apart. Transport layer, again, that's communication between nodes which need not be connected. Even network layer, which seems as if is running between nodes that are physically connected, it's not really true. So if you look at a network like this, where you see two routers connected to each other, it's often possible that these two routers are not physically connected. There is a logical connection between them. Link layer is the only layer where the communication happens between two nodes which are physically connected to each other. In fact, we saw examples where there was logical connection between two routers, not a physical connection. So the network layer was operating on a logical link. What was that example? Tunneling or VPNs. In tunneling or VPNs, the network layer was talking directly between two routers, but between those two routers, there were several other routers which are not speaking the same network layer. So even the network layer doesn't operate between two physically connected devices. The link layer is the layer which finally starts operating between two devices or multiple devices that are physically connected to each other. And because there are multiple devices that are physically connected to each other, media access control, the physical medium over which they're connected, becomes very important. And there are several different kinds of algorithms that implement media access control. So we'll start looking at that. So we know, the analogy is fairly simple. The thing to remember is it's operating between two devices that are physically connected. So the services offered by link layer: framing, link access. So framing is very simple, just encapsulating the datagram into a link layer frame. And you have to give an address to these nodes. The nodes have a link layer address, which is different from the internet layer, the network layer, or the transport layer address. So what's the address in let's say application layer communication? I'm sorry? Yeah. Well, you can think of it as a port or a socket. Sockets are the addresses that are talking to each other. In network layer communication, it is the IP address which identifies a node. Similarly, for transport layer, it's the IP address and port combination. In the link layer, the address that is used in the link layer is completely different from the internet layer or the IP address. When we are talking of sockets or ports, all of those are also associated with the IP address. A pure socket means nothing. You also have to associate the remote IP address. So the network layer, the application layer, and the transport layer all use the IP address in some form or the other. The data link layer does not use the IP address directly. It has its own addressing convention, its own addressing mechanism. And we'll take a look at that. Some link layer protocols offer reliable delivery, some don't. It depends on what are the characteristics of the medium over which these link layer protocols are operating. Link layer protocols often offer flow control. We already saw the principles behind flow control in transport layer. The way TCP implemented flow control by adjusting the advertised window. Now, error detection and error correction, we haven't really seen in detail. We saw checksums in earlier layers. So checksums was a way to detect errors. We'll go a little bit more now on how you can detect multiple errors and how you can even correct errors. Half duplex and full duplex refers to how the nodes can communicate if there are only two nodes at the end of the link. We'll also look at cases where there are multiple nodes sharing a link. One important aspect of link layer protocols is that the link layer protocol often is implemented outside the host node. It's implemented in the adapter hardware. So it's not part of the software of the node, but it's part of the adapter which connects you to the link. So the hardware comes with the link layer protocol itself. Often. Sometimes it's not the case where when we are looking at link layer protocols like PPP, which use a telephone line, there the software or the protocol is implemented at the node, but often the protocol is implemented in the adapter. So now let's start looking at error detection and correction. When we are transmitting data over a medium, when we are transmitting packets, what are we transmitting? We are transmitting bits, sequences of ones or zeros. So what are the errors that can occur? Yeah.
Transposition, deletion, and insertion.
I'm sorry?
Transposition of a bit.
Transposition of a bit. How can that occur?
If there's noise over the wire.
Oh, so bit flipping. Yeah. And the other one?
Deletion and insertion.
Okay. So let's look at a very simple scheme where you're transmitting bits in the forms of, let's say, voltages. So you transmit a high voltage, that refers to bit 1. You transmit a low voltage, that refers to bit 0. So this is bit 1, this is bit 0. Now transposition, as you said, was when this bit 1, when it's transmitted at the receiver, it is interpreted as bit 0. Now how can that happen? When there is some noise in the transmitting medium, and the noise is large enough that the receiver can interpret this 1 as 0. So now you imagine that there is some noise riding on the channel. The voltages get added up, and what the receiver is going to receive is this waveform, which is the addition of the voltage that was transmitted plus the noise that is introduced by the channel. So when this noise is so much that it can push the received signal, let's say below 0.5 V that you're transmitting, then the receiver gets confused and the receiver has to interpret that as a 0, right? But what you see here is that there is still some leeway. There can be enough noise here such that the signal is still closer to +1 than 0. So there is some margin of error in the transmission. You can introduce some amount of noise so that even the distorted signal you can recover back and claim that okay, this is a 1, not a 0. So this is basically the principle of error correction in the analog or in the modulation scheme. So this lets you correct between 1s and 0s in the face of some noise. Now what we do is we take it another level. Now we assume that okay, your analog system or your detection mechanism was not able to distinguish and it made an error. This 1 was interpreted as a 0. Now what we look at is schemes that operate in the digital domain, where you're just dealing with strings of 1s and 0s, where you can still detect and correct for errors. And the principle there is the same principle that you see here. You can tolerate a certain amount of noise and still go back to the original signal. Similarly, in the streams of 1s and 0s that you receive, you can tolerate some bits getting flipped and still go back to the bit that was originally sent. So in this scenario, what allows us to recover from the superposition of this noise? And how can we detect in the presence of noise whether the signal sent was a 1 or a 0? Using a decision level, so this 0.5 V. So this distance between a true 1 and a true 0 allows us to have some margin of error. If this 1 was in fact somewhere here, then our margin of error reduces. We cannot tolerate noise. So the idea is you want to separate your valid signals as far as possible, so that if there are some invalid signals in the middle, you can go back to the valid signal by making a guess where this invalid signal came from. So if you look at a signal that is received here, you can make a very safe guess that it was originally transmitted a 1, but some noise got added. So this is the principle with digital error correction. We're going to construct sequences of bits that can deviate a little bit, but that deviation is such that we are able to recover from the deviation. If it deviates too much, then we cannot recover. And the principle is that you try to make the distance between valid signals as much as possible, so that if something falls in the middle, you can recover. Yeah.
So you increase the maximum voltage?
Well, increasing the maximum voltage is doing things in the analog domain. that's something that you do in the modulation scheme. There are physical limits to what you can do there. You can't transmit. There are power limitations, there are modulation limitations, but that is simply trying to identify if the bit sent was 0 or 1. Now suppose that this thing fails. What was sent as a 1 you receive as a 0. Is there still some way to recover from that error? So now we are going to go, let's say, a layer above this. Yeah.
One way to first inefficient and most extreme would be to send every stream twice and then XOR them together, and if you don't get all zeros, then you can identify which bit was the error bit.
So that's what we call a repetition code.
So a very simple scheme is, instead of sending a single bit once, you send it 3 times and choose the majority. If 2 of them or 2 or more are received as 1, then you decide that okay, 1 was received. If 2 or more are received as 0, you decide okay, 0 is received. So then you can account for errors here and still have a high probability of recovering the original signal or the original bit. That's sort of the simple first level scheme. There are other schemes that are much more efficient. So let's start looking at this. So error detection and correction bits, what they do is they add redundancy to the data bit. So you transmit your data bits, and along with the data bits you are also transmitting some error detection and correction bits, and these bits add redundancy to the transmitted data and allow you to either identify or both identify and recover from errors. So let me give you a very high level explanation of how that works. That will probably let you get the intuition. Now suppose the data bits that you are sending, let's say there are 4 data bits. Okay, so 4 data bits, and since you have no restriction on the origin of these data bits or the source that is producing these data bits, these 4 bits can take any value. So the bit could be 0 or 1. So if you start writing 0, 0, 0, and let's just identify them. Now think back where you had a voltage being sent, and on that you added noise. So when you added noise, you moved the signal in the analog domain, and until you reached 0.5 V, you were still closer to 1 or closer to 0. So this amount of error you could account for and correct. Now let's see what's happening here. If this bit gets flipped, 0, 0, 0, 0, and you receive 0, 0, 0, 1, is this a valid signal or an invalid signal? Is it a valid stream of data bits or invalid? It is valid, because there is no restriction on these 4 bits. So even if any of these bits that get flipped, you cannot detect the error, because the flipped bit again refers to a valid signal. So what you want to do is somehow introduce some space between these valid data bits so that your error will make you fall in that gap between the valid data bits. That will help you identify and correct for errors. So now what you do is you add these EDC bits. So for each of these data bits, let's say you add 3 specific bits X, Y, Z, A, B, C. These bits depend on what your data bits are. Now see what happens. Now if this data bit gets flipped from 000 to 001, now the signal that you receive is going to be XYZ0001. Now unless XYZ are the same as ABC, this is not going to be a valid word or a valid signal that is sent. So the whole idea behind adding these error detection and correction bits is that you make sure that these are not identical, so that if you have an error somewhere, your error doesn't take you to another valid signal or valid stream of bits. So now if this bit got flipped, these two are not the same. So you know that this is not valid. And by choosing these XYZ appropriately, you can perhaps identify that this was originally sent as 0000 and not that 0001 was sent and these bits got flipped. So the high level idea is that you take the original valid sequence of symbols and try to introduce space between them. The way with a voltage you allow some decision threshold, you allow noise to be added. Similarly, you allow bits to be flipped, but by introducing some space, some distance between these symbols, you can detect and correct for errors. Is the principle sort of clear? Okay. So here we have an example where you have either single parity or two-dimensional bit parity that lets you detect and correct for errors. So in single parity bit, what you do is the parity bit is set as the XOR of all the data bits that are sent. So if there are an even number of ones that are sent, the parity bit becomes 0. If an odd number of ones are sent, the parity bit becomes 1. At the receiving end, what you do is you compute the XOR of everything that has been sent. If it's 0, that means you cannot detect that error. If it's 1, that means that you have detected an error, because the parity sum should have been 0. Yeah.
Just because party doesn't match, just because party does match doesn't.
So that means you have not detected the error. In the other case, you have definitely detected the error. So the absence of evidence is not the evidence of absence, but it can detect errors. It cannot detect all errors. But if there are single bit errors, that it can detect them. The two-dimensional parity works somewhat differently. So what you do here is now you arrange your data bits in a matrix. And now what you are going to send is you're going to send a row parity and a column parity. So you take all the elements of a particular row, compute the parity bit and send it, and then that way you have another row of parity bits. Same thing you do, You take all the columns of this matrix, compute the parity bit, and then you send another row of parity bits. At the receiver, now if there are parity errors, that lets you identify the row and column of the error. So now you can detect and correct for an error. So for in this example, if this was your data that you were trying to send, and this bit got flipped, then the parity error is going to show up in the right row and the right column. That lets you go back and correct the error. So this is an example where you're going to both identify and correct the error. If you are a single bit parity bit, then you can at best identify the error. You cannot correct the error. Yeah.
Parodies, you can only type, correct one input.
Uh, you can detect more than one, but under special circumstances.
No, I mean correct.
So let's see, if this bit got flipped and this bit got flipped, so you need the parity error to show up at two distinct rows and two distinct columns. In that scenario, you can detect and correct those errors. Internet checksum we have already seen how we can detect errors. There is something called CRC checks or cyclic redundancy check. So in a cyclic redundancy check, what you do is you view your data as D bits as a binary number. Depending on what D is, you're going to choose some error correcting bits or error detecting bits. And the scheme here, again, what the scheme is doing is really introducing a gap between valid data bits. The scheme is that all senders and receivers agree on a generator number G. The scheme then becomes that you choose your R error correcting or error detecting bits, capital R, such that D comma R is exactly divisible by this number G in base 2. So now what you're going to do is, given data bits D, you choose these R parity bits such that D comma R is exactly divisible by G. You transmit this on the channel. At the receiver will divide whatever it has received by G. If the remainder is 0, then no error was detected. If there is a non-zero remainder, that means you have detected error. Because in your original scheme, D comma R was exactly divisible by G. If after transmission it's not exactly divisible by G, that means an error has been introduced in the transmission. And there are schemes where, depending on what the remainder is, you can identify what D was. So the idea again is the remainder will tell you closer to which original data symbol your transmitted signal is. And this CRC check is widely used in many different link layer protocols. And how you compute those R bits? Well, what you want is D comma R to be exactly divisible by g. So n is some number or integer, g is your again another number you choose in binary. This is simply a representation of d comma r. So if you multiply data bits by 2 raised to r, what you're doing is you're just left shifting those d bits. And when you XOR that with r, you're constructing this bit pattern d comma r. So this is simply a representation of d comma r. Now if d raised to d comma r is ng, you can do an XOR on both sides. XOR of something with itself will give you nothing or 0. So we get d into 2 raised to r is this quantity ng XOR r. Now if we divide d into 2 raised to r by g, we should get a remainder r. Dividing both sides by g, we want the remainder to be r. So the way to construct those r parity bits is once you agree on this g in your transmission scheme, r is the remainder of d into 2 raised to r divided by g. And the idea behind choosing a good G is to introduce as much space as possible between these code words. So have you heard of a thing called Hamming distance? Yeah, all of you, or so Hamming distance is okay. This is the number of positions two binary sequences differ. So in this example, if you look at these three sequences, the Hamming distance between this one and this one is 1 because they differ in only one position. The Hamming distance between this one and this one is 2 because they differ in this position and this position. And the Hamming distance between this one and this one again is 2. So what this G does, or what all of these encoding schemes do, is they create a new code word such that the Hamming distance between any two pairs of words increases beyond 1. So in this, if in a pure unencoded form, what is the minimum Hamming distance between any two code words? It's 1. Because every bit sequence is valid, so the minimum Hamming distance is going to be 1. What this G does, or what most of the coding schemes do, is if you imagine your code words to be something like this, if they are unencoded, then the Hamming distance, the minimum Hamming distance between any pair of code words is going to be 1. So if one bit gets flipped, you go back, or the transmitted signal moves to another valid signal. What these schemes do is they'll increase this minimum Hamming distance between any two code words to, let's say, some value d. Or d plus 1. Let's just think of it as d. Now if there are d over 2 errors, if only d over 2 bits get flipped, then you travel a distance in this space which is still closer to the original sent signal. So if this G ends up introducing a Hamming distance of 3, a minimum Hamming distance of 3 between any two pairs of code words, then any single bit error you can not only detect but also correct, because you move only a distance 1 in any direction from any of these code words. This is still closer to this one than any other code word, because the minimum distance is 3. So that lets you detect and correct the error. Any questions? Okay, now let's start on multiple access protocols or medium access control protocols, or so-called MAC protocols. Now, in any network, you're going to get two types of links. You're going to get either a point-to-point link. So, for example, a dial-up access using a telephone line, or a point-to-point link between an Ethernet switch and a host, or you're going to get a shared link. A shared link is a shared wire or medium. So the way Ethernet used to be, or any wireless network, where all the nodes that are connected to this network are sharing this same link, and this link is considered to be broadcast. So medium access control or multiple access is very important for broadcast kind of links. So when multiple nodes are trying to transmit, how do you decide which node to allow the transmission? How do you give control to a particular node to allow transmission? So for example, we looked at routers, right? We looked at how switching is done. And you had let's say multiple input ports that want to send data to a single output port. You have a shared switching medium. In that scenario, the decision of which input port to allow to transmit was done by some arbiter which decided access or control to the shared medium. Now that scenario is a so-called centralized scenario. Why centralized scenario? Because you had these input ports, you had output ports, and you had this switching fabric. It could be memory or crossbar or whatever. Now the decision which node to allow to transmit was made by the switching fabric, but the switching fabric knew exactly who all were connected and who all wanted to transmit. So the decision is made based on complete knowledge and is done sort of in a centralized manner. Now this is true for a router, it's true for a switch, where the decision is made using complete knowledge of who wants to transmit. Now if you have a wireless medium, that laptop is connected to the wireless medium, there could be other laptops that are connected to the wireless medium, they are trying to transmit independently. Both of them are trying to transmit to this access node. The two laptops individually don't know that the other one is also trying to transmit, and the access point cannot dictate. Let's assume for now that it cannot dictate which one should get access. So in this scenario, if both start transmitting simultaneously, the signal that is received at the access point will get all jumbled up. The bits would get all mixed up, and that scenario is called a collision. So how you can allow control of the channel in a distributed setting is a very important problem, where the transmitting nodes have little or no knowledge of each other. There is no central scheduling mechanism like in a router or a switch, yet you want to maximize the efficiency or throughput of the channel, and you also want to maintain some sort of fairness. So that's the whole idea behind developing these MAC protocols. Another very important aspect of these MAC protocols is so why do you want to use this shared medium? To transmit your data and to gain access of the data. You need some kind of control mechanism or some sort of control signaling. The sort of difficult thing here is that the control channel and the data channel is the same medium. What do I mean by that? Okay, let's take an example here. Suppose you're confused about what I'm trying to explain. How are you going to ask a question? You're going to raise your hand. So multiple people raise their hands, and I'll start answering questions one by one. If you did not raise your hand and you simply started speaking, all of you simultaneously, of course nothing would get through. But by raising your hand, you're indicating that you want to transmit on this voice channel between that is shared by the entire class, and you want to gain access to it. The important thing there was your control signal was not sent over the voice channel. It was sent visually. So the control signal was sent on a separate channel. Now suppose we were all sitting blind, and you wanted to gain access, you wanted to ask me a question. So what are you going to do? All of you will start saying, I want to ask a question, I want to ask a question, I want to ask a question. And again, the signal will get garbled. To gain access to the channel, you're trying to send a control signal, but that control signal goes over the same channel. That makes it doubly difficult. Here, to gain access to this voice channel, you raise your hand, I see the visual cue, and then I give you access. So the control signal was flowing on a different channel. But with these shared media or these broadcast media, the control signal itself has to flow on the same channel, and that makes the problem even harder. So not only is it distributed, but also there is this mix of control and data which has to be addressed. Yeah, as it says here, the communication about channel sharing must use channel itself, which is a difficult problem. So what should the ideal MAC or multiple access protocol look like? Well, the ideal should have these characteristics. Let's say you have this channel which is capable of transmitting at R bits per second. When there's only one node that wants to transmit on the channel, then the channel should give the full capacity to that node. So if the channel is capable of R bits, if one node wants to transmit, it should transmit at the full rate. If there are M nodes that want to transmit, then the channel should be fair. It should give each of those M nodes an equal share of the capacity, which is R over M. The ideal protocol should be fully decentralized. No special mechanisms should be needed to coordinate, and we'll see that this becomes very difficult. And the ideal mechanism should be simple. These are all the desirable properties of ideal multiple access protocols, and we'll see different protocols that we see will achieve some of them, not all of them. Achieving all of them simultaneously is very difficult. So what are the kinds of MAC protocols? There are three broad classes. One is channel partitioning, where you take the broadcast channel, you partition it into small pieces, and you assign those smaller pieces to individual nodes. The second kind is a random access MAC protocol, in which there is no partitioning of the channel. You allow simultaneous transmissions by different nodes, but these simultaneous transmissions can cause collisions, and then you have to recover from the collisions. Then there is this taking turns protocol or token passing out of protocol, where nodes take turns to access the channel, but nodes that have more to send can have longer turns. Yeah.
Where would a token ring fit in?
One of these three classes.
Where would token ring?
It would be taking turns.
But the problem is,
Would a host, a node with more to send, not be able to take longer because
No, so if there are
Nodes which have nothing to send, they'll get the token and simply pass it along. Whereas if you have data to send, you get the token and then you send out the data. I mean, I haven't explained token ring to the class. When we get to it, we'll see. So as far as the desirable properties that we saw, let's look at 1 and 2. So in channel partitioning, if your channel is capable of sending R bits per second, if only one node is transmitting, can channel partitioning achieve desirable property 1? No, because you have broken the channel up and you have assigned a small piece to each node. So if there are more nodes if there are more pieces but no nodes transmitting in those pieces, then that part of the capacity is wasted. In random access, on the other hand, if there is a single node, then it can keep on transmitting. So in random access, if the capacity is R and there is a single node that wants to transmit, it can achieve full capacity. Fairness is a different issue. Taking turns lets you achieve a balance between these two. So let's look at channel partitioning schemes. There are two basic kinds. One is TDMA, where you divide the channel into separate time slots. And the access to a channel is in different rounds. Each node gets a fixed length slot. The length could be, let's say, the packet transmission time in each round, and each node can only transmit in that slot that it has been assigned. Unused slots will go idle. So if you have, let's say, a 6 node local area network in which only 3 nodes have packets to transmit, then node 1 will transmit in its slot in one round, and then in the next round again it will transmit in its slot. Similarly for 3 and 4, but 2, 5 and 6, since they have nothing to send but they have been allocated a slot, these slots will go idle. So you're going to waste capacity, your channel is going to be idle in these time slots. Yeah. In some ways it's the same idea. In circuit switching, you're partitioning your bandwidth into smaller portions, and the way you can do it is either use something like TDMA or frequency division, multiple access. So in FDMA, everyone can transmit simultaneously but on different parts of the channel spectrum. So again, this also suffers from the same problem. If frequency bands of nodes that have nothing to transmit stay idle, and they waste that part of the capacity of the channel. The good thing about these schemes is fairness is very easy to implement. If all of them want to transmit, then each one will get 1 over n times the capacity of the channel because of this slot allocation. So the second desirable property is easy to implement in these channel partitioning scheme. Random access protocols work this way. When any node has a packet to send, it will transmit that packet at the full channel rate R. There is no coordination between nodes in these schemes. If there are 2 or more transmitting nodes simultaneously, then there's going to be a collision. What these protocols do is, how do you detect these collisions and how do you recover from collisions? Examples of these random access MAC protocols are slotted Aloha, CSMA, CD, and all 802.11 variants are, let's say, variants of CSMA. And everything's really started from Aloha. Aloha is, you can say, the father of all random access protocols. So Ethernet, 802.11, everything is derived from the ideas behind Aloha. So Aloha was developed, not surprisingly, in Hawaii. And why was it developed? Well, what they had was, they had a number of different, let's say, islands that wanted to, they wanted to implement a scheme where these islands could communicate with each other using radio links. And they wanted the ability of any 2 pairs of nodes to communicate with each other. The way it was implemented was, these nodes would send a signal up to a, let's say, central node or a satellite on one particular frequency f1, and depending on where that packet was going, The satellite would then send that signal back using another frequency f2. But these nodes had no coordination with each other. So what could happen was these sending nodes could simultaneously be sending their packets at that frequency f1, and that could cause a collision at the receiver here when it's receiving packets from these separate nodes. F2 has no problems of collision because F2 is centrally managed by the satellite. The downlink had no collision. It could schedule F2 accordingly, but the collisions were happening in F1, in this uplink frequency at the receiver. So Aloha was developed to detect these collisions and recover from them in a completely decentralized manner. So no coordination was needed between these nodes. One way to achieve coordination could be that using this F2, you could probably send some schedule to these nodes on when they can transmit. But Aloha was developed without any need of, or without implementing a scheduling mechanism. Each of these nodes transmitted independently. And were able to utilize this channel, the F1 channel, in a distributed manner. So slotted, we first look at slotted Aloha. Slotted Aloha actually came after Aloha, but it's easier to understand. In slotted Aloha, all packets that these nodes were trying to transmit are of the same size. Time is divided into equal size slots, which is the time to transmit one frame. And the only sort of centralized mechanism that is needed for slotted Aloha is that the clocks of all these nodes should be synchronized. So all of them have the same slot boundaries. Nodes then begin to transmit frames or packets at the beginning of each slot. If two or more nodes transmit in a slot, all nodes can detect a collision. So the operation is when a node obtains a frame to transmit, when it has something to transmit, it will start transmitting in the next slot that starts. If there is no collision detected, then the node can transmit another frame in the next slot. If, on the other hand, a node detects a collision, then it will retransmit that frame in each subsequent slot with a probability P until success. Yeah.
If P is too high, can't you end up with deadlocks where
If P is too high, in fact, you can get into an unstable system where nothing gets transmitted. So the key here is to choose sort of the right P. And you look at the operation in the next slide. So you have three nodes that want to transmit packets. In the first slot, there's going to be a collision between all the three nodes. That collision is detected by the nodes, and then each of them start tossing a coin. In the next slot, it turns out that no one transmits. The P chosen and the coin chosen, the outcome of the experiment is that none of them decides to transmit in the next slot, so there is an empty slot. In the next slot, nodes 1 and 2 decide to transmit. Again there is a collision. Next slot, only node 2 decides to transmit and there is a success. And it moves on until all the nodes have successfully transmitted. And by choosing the right P, you can operate this thing in an efficient manner. Now if there's only one node that wants to transmit, it can achieve full capacity. The question is, when multiple nodes start to want to access this channel, what is the efficiency of this mechanism? Now we can see that the efficiency is not going to be the full capacity, because there'll be some slots where there'll be collision, so you're going to waste the capacity here. There'll be some slots where there's no transmission, you're going to waste the capacity there. Only the slots where you have success, you're using the channel to full capacity. So the efficiency of slotted aloha is not going to be 100%. And you can also see the efficiency is related to the P that you choose. Let's say your P is 1. If your P is 1, what's going to happen? Yeah, let's say P is, all nodes choose the same P.
So nothing will get transmitted, right?
If your P is 0, after a collision you stop. Again, nothing gets transmitted. Between 0 and 1, there is a right P that lets you achieve the maximum capacity or maximum efficiency. So the analysis of slotted aloha works something like this. Suppose you have n nodes that have frames to send, and each is transmitting in a slot with probability P. So there is an approximation here. This transmission with the probability P occurs only after there is a collision. But we analyze only scenarios where there has been a collision. So suppose each node wants to transmit with the probability P. Probability that one node will have success in a slot is going to be P times 1 minus P raised to n minus 1. So a particular node will transmit with the probability P, and all the others will not transmit with the probability 1 minus P. So the probability that there's only one node that is transmitting is going to be P into 1 minus P raised to n minus 1. Now this could happen for any of the nodes, and those are independent events. So the probability that any node has a success is going to be n times P into 1 minus P n minus 1. Right? This is the probability of success of one node. This is the probability of success of any node. So for maximum efficiency with n nodes, you're going to find a P star that maximizes this probability. That's very easy to compute. You just take the derivative, set it to 0, get a P star that maximizes this quantity. So it's a function of n. If you have many nodes, the limit of this quantity as n goes to infinity, the optimal probability is 1 over e. 1 over e is 0.37. So what that is saying is that if you have many different nodes trying to access this channel using slotted aloha, at best the probability of success is going to be 0.37, or you are going to only utilize 37% of the capacity. 63% of the slots will have either collisions or would be empty slots. Only 37% of the slots will have successful transmission. So the efficiency of slotted aloha is sort of low. You operate your channel at not even half the capacity. But this again is a worst case scenario, where the number of nodes that are sharing this channel is going to infinity. In practice, Aloha or Aloha-like mechanisms work fairly well. For instance, if you have only one node, you're going to achieve full capacity. If you have only two nodes, you don't achieve full capacity, but slightly less than full capacity. The P that is chosen should be high. So this is a very pessimistic bound, but if the number of nodes does go high, then the efficiency drops fairly rapidly. In pure Aloha, which is unslotted Aloha and which was the original mechanism, there are no slots, so there is no synchronization needed between different nodes. Different nodes are not going to share a clock. The scheme now is whenever a node wants to transmit, as soon as it receives packet, it will start transmitting. If it detects a collision, then according to its own slot, it will retransmit with a probability P. So the slots here are not aligned. Each node itself has a slot mechanism, but the slots are not aligned. So your collisions can now happen in two different ways. You can collide with a packet that had started transmitting before you, or you can collide with a packet that starts transmitting after you, while you are transmitting. In the previous case, the only cause of collision was when nodes were simultaneously transmitting. Now things can happen before you or after you that can cause trouble to you. So this is slotted Aloha, this is unslotted or pure Aloha, and it's not surprising that the efficiency of this is even worse. In fact, it's half, and you can sort of intuitively see why it's half. Your possibilities of collisions have doubled. Something behind you and something after you is now capable of colliding with you. So if you do the same sort of analysis, you achieve the optimum efficiency of pure Aloha is 1 over 2e, or simply 18%. Again, as n goes to infinity. So worst case scenario, things get bad, but Aloha and slotted Aloha really started this whole field of MAC protocols or random access MAC protocols, which let you share this broadcast medium in a distributed manner. So all the subsequent random access MAC protocols that we'll see, and all random access MAC protocols that exist today, follow the same concept of Aloha. And what is the key idea behind Aloha? The key idea is that if you detect a collision, then you let others, or you give others a chance to transmit, and you do that by using this probability P. So the key idea is that if there is a collision, then you do sort of a random backoff. You wait for a random amount of time. That randomness is decided by this probability P, or it could be an explicitly decided backoff time. But all protocols do this. If you detect that there is a problem, you randomly back off, and the hope is that the random backoff times of different nodes are different enough to allow at least one to succeed. Subsequent MAC protocols take this idea further. They keep a history of how many collisions have you seen. So if there are only a few nodes sharing this channel, then the probability of collision is low. And there the intuition is that you should not back off for a long time. You should back off for a short time. But if there are several nodes that are sharing this channel, then you should probably back off for a long time to allow others to succeed. So the length of your back off, or the length of the time that you wait, sort of depends on the number of nodes that are sharing this channel. And you try to guess how many nodes are sharing the channel by observing how frequently there's a collision. If collisions are frequent, that means there are several nodes. If collisions are infrequent, that means that there are too many nodes. So you try to optimize your number of collisions with the time that you back off. And we'll see this idea carried forward in other protocols. We'll stop here today.